Okay, so today's the start of chapter 7. We're about halfway through the semester, roughly. We want to use what we just discussed last week about electron movement, nucleophiles and electrophiles, to try to look in detail at the number of ways that nucleophiles and electrophiles react together with one another. So one common type of simple reaction is called a substitution reaction. And that's where some atom or grouping of atoms is lost and replaced with an atom or grouping of atoms. And that's what we're going to be covering in this chapter. After we do, we're going to talk about elimination reactions. So just to give you a heads up on how those work, elimination reactions usually involve eliminating hydrogen from one carbon and a leaving group from another carbon, and then replacing those two sigma bonds with a pi bond. We'll talk about that in chapter 8. We'll talk about sigma bonds versus pi bonds and specific examples of elimination reactions. So we're going to talk about some specific examples of some substitution reactions today, and we're going to look at a couple different mechanisms by which substitution reactions occur, and then we'll continue with chapter 7 on Thursday. So here's one example. I had chlorine here. I want it to leave, and I want to replace it with this nucleophile. So I know that this is a nucleophile because it has a negative charge. And I know this carbon is an electrophilic site because it has a pretty decent partial positive charge. Right? The chlorine's more electronegative than carbon. It's pulling electrons away. That creates a nice partial positive there. So the nucleophile is likely to attack at that site and push the leaving group out. The nucleophile attacking, it could occur as the leaving group's leaving, it could occur after the leaving group leaves, so there's options there, and we want to look at all the specifics involved in the most systematic way we can. We're going to look at kinetics, we're going to look at thermodynamics. I'm going to keep in mind those terms, so just a reminder, we talked about that previously. If we're analyzing the thermodynamics of this process, we're analyzing which side are we going to end up with more of when it reaches equilibrium. We're going to end up with more products or more reactants. And that's going to depend on entropy. It's going to depend on which side maybe stabilizes the negative charge better than the other side. And we can use stereo to talk about the stability of charges. And so that's the thermodynamic part. We're going to talk about that. Kinetics is about the collisions that occur. Is it possible for the nucleophile to collide here as the leaving group's leaving? Or maybe does the leaving group have to leave first to create enough space for the nucleophile to come in? Is it going to happen often? How can we facilitate the collisions we want to get the products in a reasonable time frame, right? So kinetics is all about rates and how often things happen. It's all about collisions. Can we facilitate the right collision? Thermodynamics is all about assuming we get the collisions to get to equilibrium, will we end up with more products or more reactants at equilibrium? So we want to keep those terms and considerations straight in our minds. So if we're talking about thermodynamics, which side do we think will be favored in this equilibrium? Well, we know the side that's favored is going to be determined by the sign for delta G. So if we think about the formula for delta G, the enthalpy of the process is important, and the entropy of the process is also important. So enthalpy has to do with stability. We look at which side is more stable. If we found one side has an incomplete noble gas configuration, that side would probably be much less stable, wouldn't be favored. If we can find a charge, and we can see one side has a negative, the other side has a negative, so they have the same amount of charge, but maybe if one atom stabilizes the charge better than the other, that side might be favored. So from an enthalpy point of view, focusing on the charge allows us to compare chlorine versus sulfur, right? So is sulfur better at stabilizing a negative formal charge, or is chlorine better at stabilizing a negative formal charge? Well, they're very similar in size. The chlorine does have 1 proton more than the sulfur, and so that extra proton will pull its third energy level electrons a little bit closer to its nucleus than the sulfur will. And the positive to negative ratio will be quite close in both, but the ratio is slightly closer to 1 with the chlorine. So the chlorine, being a slightly larger atom with more protons to pull and attract the extra negative into its nucleus, should be more stable. So if we're going from less stable to more stable, we can predict that if we were to look at the potential energy, which is a way of measuring the stability of the reactants versus the product, we would say that the reactants are less stable or higher in potential energy than the products. And that when this reaction occurs, there's a net release of energy. And so we can predict that delta H should be negative for this reaction. If we're just looking at thermodynamics, we can't really say much about the transition state or the activation energy or the number of steps involved in the mechanism. We're just comparing the reactants and the products if we want to know what's going to be favored when it reaches equilibrium. What about the entropy? Right? There's a reason why usually we're more concerned with the free energy change over the reaction progress than with the potential energy, because the potential energy change only tells us about the enthalpy part of the reaction. But the entropy is also important if we want to know what side the equilibrium favors. So when we're looking at the enthalpy, what do we see? Well, not much of a difference. We've got 2 moles of reactants on the reactant side, 2 moles of products on the product side, 1 of each of these, 1 of each of these. Both sides have roughly the same amount of vibrational, rotational, translational variety and freedom. And so we really can't point to any reason to think that the reactants or the products would have more entropy. So in this case, we can assume that the entropy change is probably close to 0. We'd need to know the standard enthalpies of the reactants, entropies of the reactants and products to actually calculate the value for delta S. But if we're just estimating, we can estimate it's probably quite small because the products and reactants have very similar variety in the way the structures will be moving and positioned in space. And so if this value is 0 or close to 0, this whole term, when multiplying everything together, becomes 0 or close to 0. And when I add it to delta H, it's not going to affect the value for delta H much. So the sign for delta H in most of these substitution reactions can be used as a proxy for the sign for delta G, because the other term is usually very small when you have reactants and products that are very similar in entropy. So if we're looking at delta G, we could probably predict here with a fair amount of certainty that the reactants have a higher free energy and the products have a lower free energy, and that delta G is negative because delta H is negative and because the entropy change for the system is very minimal. All right, so we know that in a substitution reaction we're going to have a nucleophile and we're going to have an electrophile, and we know the nucleophile is going to attack and the leaving group is going to leave. So the leaving group always takes the electrons with it. If this carbon were to take the electrons away from the chlorine, which it won't, but if it did, then the carbon would be the leaving group. Even though the chlorine's leaving, it has to take the electrons with it to be considered the leaving group by definition. So this is going to take the electrons away, and I know that because the chlorine ends up with those electrons in the end. If I know what the products are, I can usually predict how the arrows are moving. So that's a loss of the leaving group, and the sulfur is going to end up using one of its lone pairs to bond with that carbon. So to show that with the curved arrows, I would show those electrons moving over there, right? So this arrow is not showing that the electrons are leaving, because then the sulfur wouldn't have a noble gas configuration, right? So I have to use some chemical common sense to recognize that this arrow is indicating the electrons are being shared there, and that's going to form this new sigma bond. So we're losing a sigma bond, we're making a sigma bond, and the stability of the charges help us to recognize that the products are going to be favored when it reaches equilibrium. So this is an important point. Make sure the leaving group leaves with the electrons. We don't leave the electrons behind. So what if we wanted to show the loss of the leaving group in this step? Again, if the products are shown, you would just have to recognize what's changing to make those products. So sometimes it's helpful to draw the lone pairs in, sometimes it's helpful to draw the hydrogens in. This oxygen is going from 2 lone pairs to 3. That's what it needs to make a negative, 3 lone pairs in a bond. So it would have to take these electrons away from the carbon, and that would leave the carbon with only 3 bonds and making it a carbocation. So this is the leaving group. It left with the electrons to become negatively charged. So it's not a great leaving group, right? Oxygen's a relatively small atom. It doesn't stabilize a negative charge extremely well. So if we were trying to set this molecule up for a substitution and we wanted to replace this oxygen with something, it might be difficult to do. We might need to somehow stabilize that negative. So that's something we'll talk about later as well. Just here trying to help point out an example where you're using a curved arrow to show the loss of the leaving group step specifically. So we know any substitution reaction will have to have a loss of a leaving group and a nucleophilic attack. You may see the nucleophile, this arrow should really start here on the electrons. You may see the nucleophile attack as the leaving group's leaving. You may see the leaving group leave first to create a carbocation. And so we're going to talk about those options and which makes more sense and what conditions favor one mechanism for the other, which is a lot of what the quiz questions were about. So to be a good leaving group, it really has to meet 2 criteria. So one is that the leaving group is generally going to be more electronegative than carbon. So whatever the leaving group is, it has to have a higher electronegativity to create the partial positive on the carbon that will attract the nucleophile. The nucleophile might not come in unless there's a positive there to attract it. That positive also helps to kind of aim it and direct it in there because the opposite charges do naturally attract. Another feature of a leaving group, which students often forget, is that it has to be able to stabilize the electrons after it leaves. Right? So I'm not going to have, say for example, a hydrogen being a leaving group. Hydrogen could take these electrons and it would still have a noble gas configuration, but the negative charge that would result would create a massive charge imbalance, twice as much negative as positive, and that would be really quite unstable. So we want to, this is really the main thing students neglect. We want to really focus, we want to really focus on this. The more stable it can be with the negative, meaning the larger the atom, the less of a charge imbalance it's created, the more electronegative the atom, the more protons it has to pull the electrons closer, the better it'll stabilize that negative. And so how do we know how to judge the stability of a negative? If it can be well solvated, if it has only a -1 instead of a -2, the less charge it has. If the atom is large and electronegative, maybe there'd be resonance to stabilize the negative, or induction, or the orbital that the electrons exist in. And so we talked a lot about how to stabilize a negative charge, and we're going to apply that here to try to recognize when we have a good leaving group. We need the leaving group to be able to stabilize the negative, otherwise it won't leave. It won't leave on its own, and it might not leave when a nucleophile collides. So if the leaving group can't stabilize the electrons it leaves with, the nucleophile would have to collide extremely hard here to push it out, and that would almost never happen. So the reaction is not going to happen at a fast rate unless I have a high quality leaving group that can stabilize the negative charges when it leaves. All right, so let's talk about some examples of some good leaving groups, right? These are our 2 criteria. So one category are the halides. If I have a chlorine, a bromine, or an iodine attached to a carbon, that makes a great leaving group. Fluorine is not a good leaving group because it's a relatively small atom. Right? So if I have a carbon connected to a fluorine and the fluorine leaves, you probably think, well, fluorine is very electronegative. It's the most electronegative atom there is, so it should attract these electrons, but with only 9 protons and 10 electrons, that's 10% more negative than positive. It's a pretty significant charge imbalance, and so the fluorine isn't especially stabilized. Now, solvent effects can play a role here. If the solvent can come in and form really nice attractions to that fluorine, that could stabilize it and make it a much better leaving group. So the stability of the negative charge, it can be affected by all of the possible letters of the acronym, and solvation is one of those. So we'll keep that in mind. But generally, in most organic solvents where these reactions would occur, the solvation, the solvent's not that polar, so it doesn't really bring in large quantities of partial positive charge to effectively stabilize that. So fluorine's not usually a good leaving group. But the other halogens are big enough that their charge ratio is fairly balanced even when they carry a negative. So those are great leaving groups. For the most part, we're going to focus on these throughout the semester when we have leaving groups. But there are a couple other types of leaving groups we also want to recognize. Sulfonates are good leaving groups. So if my carbon is bonded to an oxygen that's bonded to a sulfur that has a few other things bonded to it, this could be a variety of things. Usually we think of these sulfur-oxygen bonds as having resonance, but there's a significant resonance contributor like that looks like this with no formal charge. So here, if the oxygen leaves, it's going to create a negative charge on an oxygen. And we were saying a minute ago how negative charge on an oxygen is not very stable because it's a small atom, similar to fluorine, but even a little bit smaller. Here, though, what helps to stabilize the negative is resonance. Because the negative doesn't exist on that oxygen exclusively, it can move and be spread out over all 3 of these oxygens through resonance. Each oxygen only carries a third of a negative, and so that's much more stable than a full negative on an oxygen. And so these make great leaving groups, and there are a lot of reactions where this grouping of atoms is intentionally installed on a carbon so that it can take on the role of a leaving group and leave and allow something else to easily come in and replace it. And then the third type of leaving group that's a good leaving group are water or alcohol. So in this type of situation, I've got an oxygen bonded to a carbon. This is going to be a leaving group. So if it's a water, it would have 2 hydrogens. If it's an alcohol, it would have 1 hydrogen and then a carbon group. So this could be a hydrogen or a carbon group. What makes this a great leaving group is it has a positive charge. So we're looking at the quantity of charge. Since it's already positive and highly electronegative, it's really going to attract these electrons away from the carbon. And so that creates a very large partial positive on the carbon. Each one of these does that. Some of these halogens aren't that electronegative, but they're all electronegative enough to create a significant positive. All right, so that's criteria 1. Sometimes I gloss over that because usually students have much more trouble with the second criteria. But each one of these leaving groups is electronegative enough to create a large partial positive on a carbon so that a nucleophile that's ready to share a pair of electrons come in there and connect to any one of these carbons and push out the leaving group. This one, however, because it's positive, when it leaves, it creates a neutral structure. So if the leaving group is positive to begin with, then upon pulling the electrons and becoming neutral, well, that's obviously really quite stable with no formal charge. So those positively charged oxygens with hydrogen or with an R group are also excellent leaving groups because they become quite stable upon leaving, obviously, since they don't carry a charge. So since the halides here, chlorine, bromine, iodine, and fluorine, make good leaving groups and they're involved in a lot of reactions we're going to discuss, we want to discuss how to use the IUPAC system to determine the names for molecules that have a halide attached. And we've been getting into this a little bit. I got a little bit ahead of the textbook in some examples, but basically we're going to take the steps we've already learned for determining the name of a hydrocarbon and modify them a little bit to account for situations where there's a halogen present on the molecule. Right? So anytime there's a halogen present, we got to treat it as a substituent. And we're going to order it alphabetically and give it a number depending on what carbon of the parent chain it's on. So just like any other substituent, right? If I had a methyl group there, it'd be 2-methylpropane. But here I have a chlorine instead of methyl, so it's 2-chloropropane, right? So I'm still counting the parent chain the same way. I'm still numbering the parent chain in the same way. So in this example here, I'm numbering it from the left rather than the right, because if I number from the left, the first substituent I get to is on carbon 2. If I numbered it from the right, I don't get to the first substituent until carbon 3. Right? So that's not the correct numbering. So I find the longest parent chain just like normal, number it from the side that gives this first substituent the lowest number possible, and then order the substituents alphabetically. So since the bromine is on 5-bromo, and there's a methyl on 2, and 2 methyls on 3, so 2,3,3 trimethyl. And then obviously if there's a chiral center, I would have to know whether it's a solid wedge or a dash wedge. In this particular case, prioritizing the groups gives me 1, 2, 3, and that's clockwise, so that's how I get the R configuration there. So let's look at a couple more examples, but before we do, actually, I'm going to mention, sometimes when a halogen's attached, instead of treating the halogen as a substituent, sometimes it's thought of as the parent name, and that the carbon group is thought of as a substituent. That's more of a common system. It's not part of the IUPAC system, but this type of naming is something that's still frequently used, so you want to at least be familiar with it. So if I have a chlorine here, my parent chain would be ethane, so it would be 1-chloro or just chloroethane. But if I think of the chlorine as the parent chain, I've got an ethyl group attached to it, so I could also call it ethyl chloride. Same thing down here. A single carbon would give me a parent chain of methane. I've got 2 chlorines attached to it, so it's dichloromethane. The same structure, though, is often called methylene chloride. So the chloride indicates that I've got the chlorine atoms as my parent, and then a methylene, the word methylene specifically refers to a CH2 group, or a carbon that's only got 2 hydrogens attached. So if I say methylene, that means that the carbon needs 2 more things attached to it. So a methylene chloride kind of implies that there are 2 chlorines there, because the methylene itself only has 2 hydrogens and needs 2 more bonds to stabilize it and give it a noble gas configuration. But dichloromethane, methylene chloride, same molecule, names can be used interchangeably, so you just want to be aware of that. Alright, so let's go back to looking at some IUPAC examples. So clearly here, on the one on the left, the longest chain I can make is going to be 4 carbons, so my parent chain is butane. I still don't have any double or triple bonds, so I'm still using the ANE suffix to indicate that the carbons are saturated with hydrogens. I've got a methyl on 3, an iodo on 2, and a bromo on 2. So alphabetically, it would be 2-bromo, B comes before I, which comes before M, so 2-iodo, and then 3-methyl butane. On this molecule, I'm going to skip over, got a little ahead of ourselves here. Using double bonds, actually, I'll just name this, just assume these double bonds weren't here and that these are all single bonds. because if we're using double bond, that changes the suffix, and we're going to talk about that in the next chapter. So the longest chain here is going to involve 1, 2, 3, 4, 5, 6, but if I go this way I get 5, 6, 7. So that's my longest chain. That's going to be my parent chain. And numbering it from this side obviously is correct because my first substituent's on carbon 2. If I were to number from the other side, I wouldn't get my first substituent for a little while longer. So here I've got heptane as my parent chain. I've got a chloro on 2 and a chloro on 3. So that's a 2, 3 dichloro. And that's a C alphabetically. The other group here is an isopropyl. I could call that an ethyl, a methyl ethyl, or an isopropyl. So that's whatever your preference is. And so I would then put those together to create the overall name. So 2, 3 dichloro. This isopropyl is on 4, 4 isopropyl heptane. Questions about those? There's another form of notation that you want to be familiar with. We're going to use this to try to explain what's happening with some of these reactions, some of this terminology. Typically, if a grouping of atoms of interest is attached to a carbon, you might use Greek letters to indicate which carbon and how far away that carbon is from the group. So if a group is directly attached to a carbon, that's the alpha carbon. Anything one atom away is beta, one more atom away is gamma, one more atom away would be delta, one more atom away would be epsilon, whatever's next in the Greek alphabet. So that might be relevant. We're thinking about polarity, right? Bromine's a little bit more electronegative than carbon, so it gives the alpha carbon some partial positive, and that positive attracts electrons from the neighboring carbon a little bit, not very much because it's only a slight positive, and that will make the beta carbon a little bit positive as well. So sometimes you'll see these Greek letters to indicate how far away the positive is, and based on the electronegativity difference. And when we start to see elimination reactions, the beta carbon will become relevant, because in an elimination reaction there's a hydrogen on the beta carbon, not the alpha carbon, and some kind of base will be used to pick that hydrogen up. Then this sigma bond will swing here to make a pi bond, a double bond, and that will push out the leaving group. So whatever carbon the leaving group's on is the alpha carbon, and the base will pick up a hydrogen specifically from the beta carbon. We're also going to use this terminology, primary, secondary, tertiary. These terms refer to the carbon that the leaving group or other group of interest is attached to, and how many carbons are on that carbon. So this carbon here has a couple hydrogens. It has one carbon. R represents a generic carbon group, so it has one carbon attached to that carbon that the chlorine is on. So that's a primary carbon, which makes the halogen a primary chloride. Here, the carbon that the halogen is attached to has two carbon groups, so it's secondary. So this is a secondary carbon, and this is a secondary alkyl halide. Here, the carbon that the halide is attached to has 1, 2, 3 carbon groups, so that's what makes it tertiary. So this is a tertiary carbon, and I have a tertiary halide. So you're never going to see a halide, almost never, bond to more than one carbon, right? Because it needs one bond and 3 lone pairs to balance out its formal charge and be relatively stable. So since it will only ever bond to one thing, we're not basing this terminology on how many things are directly bonded to the chlorine. We're basing it on how many carbon groups are bonded to the carbon that the chlorine is on. And we're going to see in a minute how that is very relevant, because, for example, if I want a nucleophile to come in and push out the leaving group, if I've got a tertiary carbon, well, these R's represent carbon groups, and they're probably at least the size of a methyl group, so they're probably fairly bulky. And they're going to block out the approach of the nucleophile. Whereas if there are hydrogens there and it's a primary carbon, the nucleophile should have trouble coming in there and connecting, because the hydrogens' electron clouds are much smaller and they won't repel the nucleophile's electron cloud so much when it comes in. So the primary, secondary, tertiary terminology is going to be important as we move forward, so you want to be familiar with that. So here, this chloride here is attached to a secondary carbon. And that would be the alpha carbon, these would be beta, that. Right, because this carbon has two carbons attached to it. This carbon here has only one carbon attached. So this is a primary carbon. This chlorine is on a primary carbon, and that would be the alpha carbon. This would be the beta carbon, gamma, alpha, beta, gamma, etc. Here my chlorine is on a secondary carbon. The carbon it's bonded to is bonded to two other carbons. So that makes it secondary. This would be the alpha, the beta, the gamma, and the delta. So here was the first quiz question. This first one obviously doesn't have any halides, so you just treat it the way you would any other saturated hydrocarbon. 5 carbons is pentane. I've got 2 methyls on 2 and 2 methyls on 4, so it'll be 2, 2, 4, 4, tetramethyl pentane. This molecule over here has a bromine here, so I definitely want to include that in the name. The longest parent chain I can find is 1, 2, 3, 4, 5, 6 carbons. So my parent chain there is hexane. I've got a methyl on 2 and a methyl on 3 and a bromo on 3. So bromo comes before methyl, so 3 bromo. And I've got 2, 3 dimethyl. Make sure you remember, if you have 2 or more identical groups, they both need a number, and I need a prefix to verify how many of them there are. This one down here, the longest chain I can find does not include the carbon that the chlorines are attached to. So I have to treat this whole thing as a substituent. So my parent chain has 7 carbons, so it would be heptane. And the name of this group, it would have 2 carbons in it. So it would be ethyl. If these chlorines were here, it'd just be ethyl, 4-ethyl heptane. But what do I actually have on carbon 4? It's basically an ethyl, but that ethyl on carbon 4 has chlorines attached to carbon 1 of it. So it's not technically an ethyl, it's a 1,1-dichloroethyl. So I put that in parentheses with the ethyl to indicate this whole thing is the name of the group that's on carbon 4 of the parent chain. So those of you whose quiz questions I was able to look at before today, most of you got those names nice and correct. This bromine here is on a tertiary carbon. Tertiary carbon because the carbon has 1, 2, 3 other carbons attached. Each of these chlorines is on a secondary carbon because the carbon has 1, 2 carbons attached. And so that's using the second part of the question, the primary, secondary, tertiary terminology to describe both the halogens and the carbon that they're attached to would be secondary or tertiary in these specific examples. Just to point out, there are a vast array of naturally occurring compounds and compounds that don't occur in nature but can be synthesized in the lab that include chlorines and fluorines and bromines and iodides, and they are present in a variety of different industries. And so this just gives you some specific examples, and there are many more beyond this. One other example is Teflon. Teflon is a polymer. It's just a chain of carbons, super long chain, and each carbon has 2 fluorine atoms. And that creates chains that are nonpolar, but because fluorine attracts electrons so tightly, the London forces it can create are very weak. The electron cloud is held so tightly around these fluorines, it doesn't readily shift back and forth. So it doesn't create large areas of partial negative temporarily and partial positive anywhere. So it really forms extremely weak intermolecular attractions, which is why food and other things don't stick to Teflon-coated items. And that has a really interesting and obviously useful property. So, this is really what chemistry is all about. Like, this question here is more of a rhetorical question. How does the molecule structure affect its function and properties? Well, there's obviously a ton of things that go into that. Right? Electronegativity differences, the size of the atoms, the stability of the bonds. And so when I have a halogen present, whether it's fluorine, chlorine, bromine, or iodine, if it's bonded to a carbon, it's going to be attracting electrons and creating some partial charges. So that might affect the polarity and some of the physical properties, the solubility. It'll affect the reactivity, now that we know that a nucleophile can attract and attack to that partial positive. If this halogen can leave, we're going to start to see some substitution reactions. So the presence of the halogen affects the carbon in a large variety of ways, and that's why these compounds that include halogens are useful in an array of different practical applications. So we obviously don't have time to get into much more detail than that there, unfortunately. All right, so substitution reactions. We're going to try to look at this in a fair amount of detail. First, we want to quickly review the arrow pushing patterns that we saw in Chapter 6 last Tuesday. So we know nucleophilic attack is where a nucleophile uses a pair of electrons, usually a lone pair, not always. We'll see some examples where it's not a lone pair later in the semester. But for now, usually a lone pair of electrons just starts to be shared. So nucleophilic attack is really nothing more than formation of a new sigma bond where one atom or grouping of atoms started with the pair of electrons that's going to end up being shared, and the other didn't have any of those electrons, so just both electrons end up being shared in to make that bond. We know there's a possibility of a loss of a leaving group, and when we look at these two steps in their purest form, they're kind of like the opposite, right? I can just bring the bromine in to do the nucleophilic attack and form the new sigma bond, or the bromine could leave because it's also stable with a negative. So the loss of the leaving group is similar to nucleophilic attack, but it's the opposite, right? The sigma bond is breaking. It's not breaking evenly. I'm not having one electron stay with the carbon and one with the bromine. The leaving group always takes both electrons. Otherwise, it's not a leaving group. It's some other type of reaction. The other two we talked about, these two may or may not be involved in substitution mechanisms or reactions. Some substitution reactions won't involve any proton transfers or carbocation rearrangements, but some will. So we want to make sure we're aware of that, and we'll see some examples. So remember, proton transfer is just a Bronsted-Lowry acid-base reaction where the base uses a lone pair to pick up a proton, and the acid keeps the electrons behind, so the proton ends up being transferred to the base. Carbocation rearrangement, we want to remember the types that are involved. It's either a hydride, which is a hydrogen with a pair of electrons, or a methyl, which is obviously a CH3 group with a pair of electrons. It's taking the electrons and shifting them over one carbon, right? So the rearrangement is only going to be one carbon away. It's never going to occur multiple carbons away. It's always going to be a methyl or hydrogen shifting. And the point of that is to stabilize the carbocation. So last time we talked about hyperconjugation and how when a carbon that's a carbocation is on a primary or secondary site, there's a hydrogen here. And that hydrogen doesn't have much electron density to donate in to the positive to help stabilize it. If I have a positive on a tertiary carbon, it's usually more stable because the carbons that are attached can rotate a sigma bond, whether it be a CC sigma bond or a CH sigma bond, into the same plane as the empty p orbital here. And so donating electron density into that p orbital by rotating the sigma bond into a position where it's parallel with that p orbital really helps to stabilize that positive charge because more electrons move around that nucleus and stabilize a little bit. So the more hyperconjugation you can do, the more stable the carbocation. And that is why less stable carbocations will undergo one of these two types of rearrangements to form more stable carbocations. And don't forget, what stabilizes a carbocation most is resonance. So sometimes a methyl or hydride shift might occur to put the carbocation one carbon over if that allows it to be stabilized by resonance specifically. Any questions about any of that? All right, so as we were saying, every nucleophilic substitution reaction that we're going to talk about is going to involve a nucleophilic attack and a loss of a leaving group. There may be proton transfers, there may be carbocation rearrangements, it depends on the specifics, but there's definitely going to be both of these occurring. And so the question then becomes, what order do they occur in? Does loss of the leaving group happen first? Does nucleophilic attack happen first? Do they happen at the same time? And so that's what we want to look at in detail. So there are really three possibilities we could even imagine. One would be nucleophilic attack happens first, and then loss of a leaving group. So if I were to draw that, I would have the leaving group here, I would have nucleophile, the nucleophile would attack, now it would be bonded there, and then the leaving group would leave, and that would give me my product. Is that reasonable? Is there anything unreasonable about that?
Can't that create a 5-bond carbon?
Yes, right. And so this is, again, students will do this by mistake sometimes. You really want to get into the habit of drawing in the other bonds. And Krishna's correct here that this will typically be 3 bonds plus a fourth to the leaving group. So I can't bring in a nucleophile and create a 5-bonded carbon. So if the nucleophile is going to attack it first, this can't be the mechanism. The leaving group would have to leave at the same time. And so that's really option 3. The nucleophile can attack as long as the leaving group leaves at the same time. I can avoid the 5-bonded carbon that would otherwise occur there. And that's definitely something that's not going to happen. I'm not going to get a 5-bonded carbon. Very good. So the other option is the loss of the leaving group first. So we can consider that option. Here's my leaving group. It leaves first. If it leaves, now I'll have a carbon that only has 3 bonds. So in a second step, the nucleophile could come in and attack and then end up bonded there. And so we're going to see a little later how, depending on what's attached to the carbon, we may get the leaving group leave first to create a carbocation, Or we may see the nucleophile attack first. And so the biggest factors that determine which happens is sterics and the stability of the carbocation. And so we're going to talk about this in detail. Just wanted to mention, generally, if the groups attached here aren't too big and their electron clouds aren't too big and they don't block out the electron cloud of the attacking nucleophile, then usually this type of situation where the nucleophilic attack and loss of leaving group happen at the same time is possible. If those groups are too big, if they're all carbon groups, it's too crowded and the nucleophile can't come in. The nucleophile would have to wait for the leaving group to leave, and that would create a carbocation. If the carbocation has hydrogens bonded to it, as we just said, those cannot stabilize the carbocation through hyperconjugation. So that would be pretty unstable. So that would make it much less likely for the leaving group to leave behind the carbocation, in which case it would be more likely for the nucleophile to come in as the leaving group's leaving. Right? So those are some of the important considerations we're going to see here moving forward. So we definitely want to verify, though, experimentally as much as we can, what is happening so we can understand it and facilitate it. Right? If I want to do this reaction and I want to make some compounds, I want to make it in the highest yield possible. I want as many of these collisions to occur as quickly and as cleanly to give me a pure yield of a product in a reasonable time frame. So I want to understand the reaction in as much detail as possible if I want to maximize the use of the reaction to make some compound. So this is called an SN2. It's a substitution reaction. I'm substituting the leaving group for a nucleophile. It's nucleophilic, meaning there's a nucleophilic attack occurring. And the 2 here refers to the fact that it's second order overall. It's confusing because this process is occurring in one step. And I remember when I was first taking this class, I constantly would get it mixed up. Because to me it seemed more logical to have it be SN2 if it were a 2-step process, and SN1 if it were a 1-step process. But that's not correct. The 2 means that it's a second order rate law overall. And when we talk about SN1, that means it's a first order rate law overall. So when we're writing the rate law, it's always going to be rate equals the rate constant times the concentration of my reactants. And the exponents have to be determined experimentally. If you know the mechanism, though, you can predict what the exponents should be if that mechanism were actually occurring. And that's based on the collisions. Right? So we have to remember, what does the rate represent? It represents how much product can be formed per second. And that depends on how often the reactants undergo effective collisions in which bonds form and break to produce that product. So in this rate law, it's second order specifically because both reactants are involved in the collision. There's a 1-step process where both reactants have to collide with one another. The nucleophile has to come in and collide with this carbon at the same time the leaving group has to leave. So these 2 molecules have to collide specifically with one another. That means if I have a reaction, the more nucleophile I put in and the more electrophile I put in with the leaving group, the more often things will start colliding. So if I increase the molarity of either one of these to facilitate more collisions, that will have a proportional increase in the rate of product production. If I double the amount of nucleophile, the rate should double. If I double the amount of electrophile with the leaving group, the rate should double. Because doubling the amounts of either of those present is going to double how often collisions occur, and I'll get a proportional increase in how often those collisions can produce the product. So that's why they're both first order, and when I add those together, 1 plus 1, I get second order overall. So that's why it's called SN2, because it's second order. So how would I design an experiment to test that? And that's part of what one of the quiz questions was asking about. I'd have to be able to measure the rate. I'd have to be able to measure the molarity, the brackets mean molarity, of the nucleophile and the electrophile. And I'd have to set up 3 experiments. I'd start with some molarity of both, measure the rate. How do I do that? Well, I would plot how the molarity of maybe the the electrophile, plot the molarity of the electrophile over time. And I would measure in the beginning of the process, in the very beginning, what's the slope of this line? The faster the reactant is consumed, the faster the product is produced. So I could measure how many moles per liter of this react in the first second or two, and that gives me the initial rate. And so I'll just make up a number, let's just say it was 10 millimolar per second. So then if I double the molarity of the nucleophile and keep this one the same, then I'm testing this idea that it should be first order, right? Because if I had twice as many around and they collide twice as often, that should produce product at twice the rate. And so if I do indeed see a doubling of the rate, that means that the nucleophile is first order, right? Doubling this will only cause the rate to double if this is to the first power, because 2 to the first power is 2, and I have to keep both sides equal. I have to multiply both sides by 2. Likewise, if I go back to 1 molar here and double the concentration of the other one, since they're both involved in the collision, doubling the amount of either one of them should increase how often the collisions between them occur. And so if I double the molarity of this, and its exponent is also a 1, to keep things equal, this side would have to be doubled as well, or 2 to the first. And so that would cause the rate to double as well, millimolar per second, if it were also first order. So both are first order, and I can verify that experimentally because in doubling the molarity of either one would cause the rate to double, because it would cause the number of effective collisions to double when I put more molecules in a given amount of space. So that's one way to confirm an SN2. So we talked about this here already. What about stereochemistry? Well, experimentally, we can also verify the SN2 reaction using stereochemical information. So if I start with my leaving group attached to a chiral center, if it were to leave first, just for the sake of argument, what would be formed is a carbocation. And a carbocation is flat. A carbocation has an empty p orbital that has a symmetrical shape. So when the sulfur goes to attack the carbocation, it could come in and overlap here, or it could come in and overlap here with equal probability. So there'd be no spatial positioning of the sulfur on the carbon for every molecule. Half the molecules would have the sulfur coming in and connecting to create a chiral center with the sulfur coming off the top of the carbon, and the other half would have the sulfur coming in and overlapping and bonding at the bottom of the carbon. So I would get a racemic mixture in that case. We'll see another example of that here in a minute. That would be if I were doing an SN1. But back to the SN2, since the SN2 requires 2 molecules to collide simultaneously, the sulfur would have to come in and replace the bromine. And the way this works is the sulfur cannot come in on the same side as the bromine when the bromine is leaving. And the reason for that has to do with the orbital. So we'll see why that is in a minute. The sulfur has to come in from the back side, 180 degrees away from where the leaving group's leaving. So that means when the sulfur is coming in, this methyl and hydrogen are going to flip to the other side, and the product we're going to end up getting here, so the hydrogen will still be pointing out at me, and the methyl group will still be pointing away, and the ethyl group will now be here. The sulfur will come in there and connect over here. So I will create a pure chiral product, assuming that this center was a chiral center. When my nucleophile comes in, if it is an SN2 mechanism specifically, the nucleophile will have to come in 180 degrees away from where the leaving group left. And that will create a very specific spatial arrangement for how these groups are positioned. So how do I verify that that specific spatial arrangement has been formed? Well, I can measure the optical activity. If it went through this other mechanism, then the sulfur could come in on one side half the time and on the other side half the time. That would give me a mixture of two different products. I would get this one here, and I would get the other one, right? Because when the bromine leaves, once it's gone and the carbocation forms, the sulfur could come back on the same side where it left. It doesn't have to always come in on the opposite side. So if it came back in on the same side, I would get a structure that looks like this. And these two molecules are enantiomers. So when the SN2 mechanism is the one that's occurring, the nucleophile has to come in on the opposite side from where the leaving group left, and I get one enantiomerically pure substance. If the leaving group leaves first, and I get a carbocation, then the nucleophile can come in from either side, where the leaving group left from, or from the opposite side, and in that case I get both of the enantiomers. And so if I put that product through a polarimeter and measure the optical activity, if I'm only doing the SN2, I have an optically pure sample. I should get, it would either be an R or an S configuration, and I would either get positive or negative rotation of plane polarized light, which would be measurable. But if the SN1 mechanism is occurring, the bromine leaves first, I get the carbocation, the sulfur comes in on the top half the time, on the bottom the other half the time, then I get a mixture of both of these compounds. Well, since they're enantiomers, if I put that in the polarimeter, shining plane polarized light through a pair of enantiomers is going to give me zero optical activity, because one enantiomer will rotate the light one way and the other will rotate it back the other way, and it will cancel out. So we're saying the backside attack has to occur because of the orbitals, and that's explained here. Basically what we're saying here is that the nucleophile is not going to attack on the front side. So there's, if we just look at the electron cloud there, if this is my leaving group, it's a cloud of negative charge, right? These orbitals has electrons and they're all full of negative charge. So for the nucleophile to try to come in on the same side, it would be repelled. Right? The bromine's more electronegative than the carbon. It's carrying a partial negative. The nucleophile is either negative or it has a partial negative, and those would repel. Right? So the nucleophile is not really attracted into the same side that the bromine's leaving anyway. Right? So that's one argument for why it has to come in from the back side. The other argument is an orbital argument. So what this orbital argument is saying is that the nucleophiles, electrons that are in this molecular orbital that's occupied, so this is the highest energy occupied molecular orbital. And so we're talking about the nucleophiles. Lone pair usually is in an atomic orbital or a molecular orbital, but it's occupied with electrons. To make a bond, I can only have two electrons in the area of overlap when the molecules come together. So I've got 2 electrons in this orbital of the nucleophile. It has to come in and overlap with an empty orbital of the electrophile. So the lowest energy unoccupied molecular orbital is shown here, right? So when we talked about molecular orbitals, we said, I don't expect you to predict the shapes or electron density in all the molecular orbitals, but those can be determined by computer simulation, right? So that's what we're seeing here. These red and blue areas represent one orbital. That orbital is empty. That empty orbital represents the area where electrons from the nucleophile can come in and overlap. And the problem is here, there's a node in this empty orbital. And so if the nucleophile were to come in and try to overlap with the carbon on this side, there's a node here. It wouldn't be able to effectively overlap between the full orbital and the empty orbital and get those 2 electrons into a nice molecular orbital if when the orbitals come together there's not much overlap because of the node. But there's this nice fat area where the nucleophile can come in and effectively overlap its orbital with the existing empty orbital in the backside. And so the backside attack is always going to occur to facilitate the correct overlap and facilitate the total of 2 electrons existing in the area of overlap that will create a new molecular orbital and a sigma bond between the nucleophile and the carbon. So there definitely has to be backside attack. We know that theoretically from what we're just talking about here, and we know it from the experimental results. We know that if we can get an SN2 to occur, the stereochemical outcome matches with this theoretical prediction that the nucleophile has to come in from the opposite side, 180 degrees away from where the leaving group's leaving, if it is going to be an SN2, if it is going to come in at the same time that the leaving group leaves. So that then allows us to imagine what the transition state would look like. So remember we said the transition state is the highest point in this energy diagram. So if we looked at free energy over the reaction progress, here's my reactants, the SH minus and the electrophile. Here's my products, the Br minus and the resulting substitution product. The products are lower in energy than the reactants, as we said, because the negative charge is a little bit more stable on the bromine than the sulfur, so those will be a little bit lower in energy. The entropy difference is minimal, so we're looking at the enthalpy difference or the stability difference between those negative charges to judge which one is going to be favored when it reaches equilibrium. If this is an SN2, it's a one-step process, so there's only one transition state, one hill. The sulfur collides with the electrophile in one step. Here it is shown. It's colliding in the backside, pushing out the bromine. All that's happening at once. So the bond that's forming is happening at the same time as the bond that's breaking. And that's what the transition state shows. The transition state occurs here at the highest energy point. That's the point where the electrons are not in proper orbitals. Right? So to begin with, the electrons are in this nice sp3 orbital, held relatively close to the nucleus. In the end, they're in a sigma bond, also held close to the nucleus, nice and stable. And that's why the beginning and end is more stable than the transition state. For the other pair of electrons, in the beginning it's in a nice sigma bond, in the end it's in an sp3 orbital that's also relatively stable. So that's why the reactants and products are much lower in free energy than the transition state. What's happening in the transition state is this pair of electrons is not really existing in a lone pair orbital. It's also not in a sigma bond orbital yet. It's not in a proper orbital. It doesn't have the ability to attract effectively to either of these nuclei. It's in this kind of stretched out area. So the elongated dotted line represents the instability of the electrons when they're not close to the orbitals. And so that is true for the forming bond as well as for the breaking bond. This carbon-bromine bond starts to stretch, and once it reaches a point where it's too long, the electrons are no longer in the sigma bond, but they haven't fully left with the bromine to exist yet in the lone pair, and so they're not in a stable orbital, and the elongated dotted line there also indicates that. So it's important to be able to show transition states and to draw what they look like and to understand that any bond that's breaking or forming is going to be really unstable during the transition state, and that's the highest energy point of the reaction. You also want to be able to draw in where charges exist in the transition state. So for this carbon here, we're not showing any partial charge on it. Right? The transition state is a transition between the reactants and the products. It's basically what the substance looks like partway between what it looked like on the reactant side and what it looks like on the product side. So if we look at that carbon, it starts off with 0 formal charge and it ends up with 0 formal charge. So at no point is that carbon carrying any charge. The new electrons are coming in at the same time the old electrons are leaving. So we don't need to show a partial charge there. However, if we look at the sulfur and the bromine, we see something a little bit different. We see that the sulfur starts off with a negative and ends up with 0 formal charge. So transitioning between a -1 and a 0 is somewhere between -1 and 0. So any atom whose charge is changing during the collision will have some quantity of a partial charge, usually a fraction of a charge between the two different states that it exists in before and after the reaction. Same thing with bromine. It's starting off with 0 charge, it ends up with a -1, so it's starting to pull enough electrons away to exist with the negative, but it doesn't have them all yet, so it's not a full -1 yet. And these charges are really important because what we're going to see on Thursday is that during the transition state, which is really unstable, part of what makes it unstable is these charges. I mean, the main thing that makes it unstable is the electrons that don't exist in proper orbitals. But in part, it's a little bit also unstable due to these charges that exist. So a solvent molecule, like for example water or something, that has some partial charges, it could come in and form some attraction. And we want to look at what solvents will help facilitate this reaction, right? I want to convert this into the products. I want the sulfur to attack and push out the bromine. These are the products I'm trying to make. If I want to run this reaction, I'm trying to make these products. So if I want to make these products, I want it to happen quickly. I don't want a really high transition state so that almost none of the collisions can make it over. I want to stabilize the transition state to facilitate the process. And so recognizing that the transition state has some charge allows me to understand that I want a solvent that's polar so it can bring in some opposite charge to stabilize these charges during that moment. If I can stabilize them, the energy will be a little bit lower. It doesn't affect the energy of the reactants or products, but if the solvent can stabilize the charges that occur in the transition state won't be so unstable. And then a higher percentage of the collisions that occur will have the energy necessary to make it over, and I can make more product in a given period of time. So thinking about the transition state allows us to think about how we can stabilize the transition state, which allows us to form more product in a given period of time. As we were saying before, kinetically, if the site where the leaving group's attached has too many carbon groups, the reaction won't work. For the nucleophile to attack from the back side, it would have to figure out how to get in here past all these massive groups with electrons that are repelling the new electrons and preventing them from coming in. So it would have to come in the back side and push out the bromine, but when there's other groups in the way, that is it's too infrequent that the collision would occur to even measure. You can let that go for a long, long time, and you won't see any product formation, because every time the nucleophile is about to collide in the right spot, one of these methyl groups is in the way and blocks it out. If I only have two methyl groups and a hydrogen, that hydrogen is small enough, now the nucleophile can make it in there and push out the bromine once in a while. But the other methyl groups will block it out a lot of the time. So the number of effective collisions isn't very great. Right? So we're just setting this to 1 to compare the other values to it. So if we set that to 1, we'll see that having only one methyl group means it's even less crowded, and that will happen 100 times as often. If all of them are hydrogens and there's no real big carbon group to block out the nucleophile can collide in here quite readily and push out the leaving group and do an SN2 at a rate that's greater than 1,000 times faster than it would be if there were two methyl groups. Right, so this is all about sterics. As we're saying, if the site of attack is sterically blocked, then there are going to be very infrequent effective collisions, and the rate of product production is going to be very, very minimal. And that trend also confirms the mechanism that we're talking about. And so everything here is in a cohesive story that's all pointing to the same mechanism and the same transition state. We were already pretty much talking about this. Just to reiterate, kinetically, we're talking about how can we stabilize this transition state? How can we get the reactants to collide to make the transition state as often as possible? So if we bring solvent in that can form some attractions here, that can make the transition state go through a lower energy. If we can put more moles per liter of our two reactants in there, it'll help them collide more often. So more of the collisions will have the energy necessary to get over to the product side. Right? Those are kinetic arguments. If we increase the temperature, the collisions will be stronger and more forceful, and they'll be able to make it over to produce the transition state more often. That's all kinetics. Thermodynamics doesn't care about the pathway. Thermodynamics is only a comparison between the reactant energy and the product energy. And if we're looking at free energy, then we can say that if the products are lower in free energy, then delta G is negative and the products are favored when it does reach equilibrium. So if the transition state energy were too high, it might produce so little product that we never get to equilibrium over the course of a day or two or a week or a month or a year. So the thermodynamics are only really relevant if we can get to equilibrium. And so these two are different analyses, but they work hand in hand. I can't get to equilibrium if my kinetics don't allow frequent enough collisions that will produce the products. But even if the collisions happen often and I produce a lot of the products, if the product were much higher in energy than the reactant, well then when it is produced and it reaches equilibrium, I would get mostly reactants. So if I want to make a reasonable amount of product in a reasonable period of time, I have to look at both of these factors. I have to look at, is the transition state energy low enough and the conditions such that they'll have some effective collisions that can make it over there and produce a reasonable amount of product in a given period of time. That's the kinetics. And also, are the products stable enough, or do they have enough entropy so that they're lower in free energy than the reactants, so when it does reach equilibrium, I'll get a significant amount of the products present. And so that's the value of reaction coordinate diagrams. And so here are some diagrams that illustrate what we were just talking about. We were saying how when I've got more carbon groups, it's harder for the nucleophile to get in. So that affects the energy of the transition state. Right? Each one of these reactions starts at the same energy. And each one of these reactions produces products at the same energy. So the difference here is not a thermodynamics issue, it's a kinetics issue. The only difference between these three examples is the height of the transition state. And when there's very little sterics crowding out that collision, during the collision, when the nucleophile is coming in and starting to form a bond to that carbon, and the leaving group is starting to leave, if all I have here are hydrogens, well, their clouds are small. It doesn't crowd out the nucleophile much. It doesn't create much repulsion. If there isn't much repulsion, then it's still relatively stable, even though the bonds are in the process of breaking and forming, which is kind of unstable. But if I put R groups in here, and I've got these methyl groups, well, then the electron clouds are much higher, much larger. So during the transition state, the cloud of electrons around the nucleophile will get too close to the cloud of electrons on these methyl groups or R groups and start to cause repulsion. And so if there's repulsion and it makes it unstable, then it's going to be higher in energy during the transition state. And so that's not going to happen as often. Right? So these reaction coordinate diagrams explain the relative rate of product production depending on how sterically hindered the site is where the nucleophile has to attack. And if I have methyl groups or R groups at all three of those positions, it's too crowded for me to even measure any product production in a given period of time. So the tertiary substrate reacts too slowly to even measure. So we can't measure how high its transition state is, but we could say it's definitely much higher than the secondary, primary, or methyl. So it's important to understand the details here and not just memorize the rules, right? If we were just memorizing this, we would say, well, tertiary is too slow to measure, secondary is pretty slow, primary is really fast, and methyl group's even faster. If we just memorize that, though, we might make a mistake, and I just want to use this example to illustrate that. So neopentyl bromide, let's draw the structure of that. Neopentyl, it looks like this. Oops. Well, this would be my bromide. So this is a neopentyl group. There's 1, 2, 3, 4, 5 carbons. So this is neopentyl bromide. Is the bromide on a primary, secondary, or tertiary carbon? Well, the bromide is on a primary carbon because there's only one other carbon group attached to it and there's 2 hydrogens. And if we just go by what we saw in the last slide, we would assume that it should react readily by an SN2 pretty quickly. Because what we were just saying was, if it's a primary site, it's not too crowded, the nucleophile can come in, a lot of effective collisions, we get a pretty fast reaction rate. And that for a primary carbon, the transition state energy isn't very high. But in this particular case, because the R group attached here is very crowding, it's an especially large branched group. If we were to look at the carbon where the nucleophile has to attack, even though 2 of the things attached here are hydrogens, the third thing is this large branched group. And its electron cloud is very, very big. So the ability for the nucleophile to come in here and do an SN2 and push out the leaving group is not very good. So all the repulsion that would exist between the nucleophile and this big electron cloud during the attack is going to make this very unstable. So even though it's a primary carbon, if one of the groups attached is especially large, it might behave more like a secondary or even more like a tertiary carbon because of the large electron cloud blocking that out and creating repulsion during the transition state, making the transition state even higher, so they're much less frequent effective collisions. And so kinetically, I can't form much product. Once the product's formed, there's nothing unstable about it. Once the nucleophile replaces the Br-, it's not a problem. So thermodynamically, this might still greatly favor the product side, especially since Br- is pretty stable. If the nucleophile was really unstable with the negative, thermodynamically, I'd get way more products than reactants. But kinetically, if the collisions can't be facilitated, I'm just not going to form significant amounts of products in any given period of time. So that's why it's important to think about both. And rather than memorize rules, rather than just memorize that primary is always faster than secondary, which is always faster than tertiary by SN2, we want to understand the actual concept so we can look for exceptions and recognize that even one large crowding group is going to make a big effect on the attack of that nucleophile on the substrate. So that leads us to the first quiz question, which was focused around SN2. What are the best reaction conditions? On some of your quiz questions that I looked at early on, I got a little ahead of where we are here in the class, and I asked some of you to describe necessary solvents. But we aren't actually going to talk about the solvent effect until Thursday. So when I grade your quiz questions today, I'm not going to take off points if you don't describe the solvent effects, since we're not really covering that today. That wouldn't really be fair, obviously. So there is a way to select a solvent that will favor an SN2 mechanism versus an SN1. But we're going to talk about that Thursday, so we're not going to worry about that right now. So to facilitate this reaction, if we want an SN2, though, one important point is we want a strong nucleophile. What does that mean? A strong means unstable. It means that it's very readily likely to start to share its lone pair of electrons, and it probably has a full negative. So something that really needs to share its electrons so that it's already starting pretty high in energy. It's relatively unstable to begin with. That way, when it does collide to create the transition state, there won't be a big activation energy necessary. Most of the collisions will have the energy necessary to get to the transition state if we start with something that's already unstable. If we start with a weak nucleophile and it was more stable in energy, then most of the collisions wouldn't have the energy to get to the transition state, and most of the collisions it would just bounce off. So strong nucleophile with an unstable negative charge, and we would want to have a high molarity of both the nucleophile and the substrate. Because in the SN2, they collide at the same time. The nucleophile comes in at the same time the leaving group leaves. So having more of either of them will create more frequent collisions, and that will make more product in a given period of time. So not only the energy necessary in the collision, but the frequency of collisions based on their concentrations in solution will help get to the transition state and produce the product. Also, by using an unstable nucleophile, which starts higher in energy, there's more of a chance that thermodynamically the product will be more stable, and that when it does reach equilibrium, I'll get more products than reactants. So those are the main things there, in addition to the solvent, but that's not really something we're talking about till Thursday. So what about experiments? Well, we talked about that already. We said one experiment you could do would be to measure the rate law. If you can show that the rate depends first order on the concentration of the nucleophile and also first order on the concentration of the electrophile, that wouldn't necessarily confirm that it's SN2, but it would at least correlate with an SN2 mechanism. There could be some other mechanism that we haven't imagined that could be at play that would also create a first order situation for both of these, but no one's thought of anything yet, so it's probably unlikely. So that does at least suggest it could be an SN2 reaction, because if both of these have to be involved in the collision, then increasing the molarity of either one will increase the rate proportionally by creating more frequent collisions between the two of them. So measuring the rate law and verifying that they're both first order is one way to show that it's second order overall. Secondly, we could use the stereochemical data. So if this reaction is an SN2 specifically, then we said the nucleophile has to come in from the backside from where the leaving group's leaving. So once it's in there, every molecule would end up with the nucleophile with a dashed wedge here, right? The chlorine's pointing out at you. The nucleophile has to approach from behind the molecule, from behind the screen if the chlorine's pointing out towards you from the screen. And if it has to approach from behind the screen, it's going to end up connecting there with a dashed wedge. If every molecule has this stereochemical outcome, and none of the structures end up with the nucleophile coming out at you, that would confirm the SN2 mechanism, that the attack had to occur from that orientation, and all the products end up with that specific orientation. So how do we verify that experimentally? We would measure the optical activity, right? So if I had a mixture of both of these, then the optical activity would be zero because they'd be enantiomers and they'd cancel each other's optical rotation. But if I only get one, especially if I know what the molecule is and I know what this pure enantiomer, what direction and to what degree it should rotate the plane polarized light, I can verify that is the correct enantiomer that formed experimentally. Any questions about that? Alright, so that covers the basics of SN2. We're going to talk more about the competition between SN2 and SN1 later, but we want to cover some of the basics of SN1 first. As we're saying, the SN1 mechanism, it's also a substitution reaction, so I'm losing the leaving group and replacing it or substituting a nucleophile for it. And the N stands for nucleophile, so we're using a nucleophile to push out the leaving group. And the 1 here means that it is first order overall in the kinetics. And so if we do this reaction, and it's occurring by this mechanism where the leaving group leaves first to create a carbocation, and then the nucleophile attacks, in terms of the rate law, the rate only depends on the concentration of the substrate to the first order, and that the concentration of the nucleophile is actually 0 order. So if it's 0 order, we usually don't even write it, because anything to the 0 power is equal to 1, and multiplying by this by 1 is not going to affect it, so we just often leave that out. So why is the nucleophile 0 order? Well, if we look at the reaction coordinate diagram, and we start with our electrophile, and the first thing that's going to happen is the loss of the leaving group to form this carbocation. The first step that forms the carbocation might look something like this. Then the nucleophile can attack in a second step. So anytime a bond breaks, I have to get to a transition state because the electrons in that bond breaking are really unstable for an instant. And anytime a bond forms, I get to another transition state. So in this case, it turns out that the second transition state doesn't go up as high as the first one. So that means since the second transition state is lower in energy than the first one, the first step is the slow step. That's the one that's determining the rate of product production. It's like an assembly line. If you're the first person in line and you're moving really slowly, the next person after you doesn't have anything to do until you hand them what you've accomplished on your part of the assembly line, and then they can work with that and continue on down the line. But if there's a bottleneck in the process slowing it all down, everything depends on that first step. And that's the case in an SN1 mechanism. So loss of the leaving group to form a carbocation, it's not easy to do, right? A carbocation is really unstable. So trying to pull the electrons away from that carbon, it takes a really high energy collision, and it's really unstable in that moment as the bond starts to break. So that's the slow step. And what that means is, it doesn't really matter how much nucleophile I have present. Adding more nucleophile only facilitates the collisions here in the second step. Adding more nucleophile will allow the second step to occur more often because the nucleophile is involved in a collision in the second step. Adding more nucleophile will not facilitate loss of the leaving group. And that's the step that's slowing everything down. And so that's why the nucleophile is zero order. If I double the amount of nucleophile, there's no effect on the rate of product production because I'm only speeding up the second step. So the rate would just be 1 times its normal value because 2 to the 0 power is the same as multiplying by 1, and to keep it equal, the rate would be equal multiplied by 1. But since the substrate is first order, obviously if I add more of the substrate, more molecules of that in a given amount of space are going to be colliding more often. The more frequently they collide, the more frequently the collisions will have enough energy to make it to the transition state. So the molarity of the substrate does affect how often the first step occurs, and so adding more of that, if I double the amount of substrate, I'll double the rate because 2 to the first power is equal to 2. So I get a totally different, not totally different, but I get a different rate law in an SN1. I get rate equals the rate constant times the molarity of the compound with the leaving group. The nucleophile does not affect the rate. And so here's the reaction coordinate diagram. The carbocation intermediate is right here. I'm forming 2 transition states. In the first transition state, the leaving group is starting to leave. It's starting to pull the electrons away with it. And so it starts to become partial negative. The carbon starts to take on a partial positive as the electrons leave. Once the leaving group fully leaves and stabilizes the electrons again, it's a little bit lower in energy than it was before, because here at least the electrons are in an orbital. Here they're not really stabilized in an orbital. But then the nucleophile has to come in a second step. So the transition state in the second step would have the nucleophile coming in and starting to form that bond, so its negative would start to go down. If it started off as a full negative, as it starts to share, it would only be a partial negative. But again, during that moment of the collision, the electron pair is not in a proper orbital because it's starting to form in a new bond, but it hasn't yet formed yet. And so that's again another relatively high point in the energy of the reaction. But as we said, the transition state of the first step is higher than the second step. So that's the slow step. If we want to make more products, we got to concentrate on facilitating that first step. We talked about that. Which step is the rate determining step and why? We already said it's this first step. Why? Because it has a higher transition state energy than any other step. Why does the rate depend only on the electrophile molarity, not the nucleophile molarity? That has to do with the fact that the first step is a slow step and that the nucleophile is not involved in that step. And so anytime I want to make a process happen more often or faster, I have to facilitate the step that normally is slowing the whole process down. I have to make more collisions. And this is the only thing involved in a collision in that step. So the only way to speed it up would be to add more of this substance to facilitate more collisions involving this substance per second. The collisions involving the nucleophile won't help because they don't occur until after the first step has already occurred. We talked about this. Substitution with the nucleophile. That's first order overall. And it's first order overall because the nucleophile is zero order and the electrophile is first order. Alright, so we've talked about both mechanisms. Let's just do a little comparison here before we end. Answer a couple questions, make sure we've got this down. So let's say I've told you that the mechanism is an SN2. If it's an SN2 and I were to triple the molarity of the nucleophile, what effect would that have on the rate? Well, if it's an SN2, then the rate law includes both the nucleophile and the electrophile, and they're both first order. So if I were to triple the nucleophile molarity and it's first order, That means I'm multiplying the side by 3 to the first power. To keep it equal, the rate would have to be multiplied by 3 to the first power. So the rate would triple. Why is that? Because in an SN2 reaction, both substances have to collide with one another in the only step. Any increase in molarity of the nucleophile is going to help those collisions occur more often, and it's going to help produce the product more often. So the rate of product production increases at the same rate that I add more and more of this to increase how frequently the collisions occur. Alternatively, if it's an SN1 reaction, in that case, when I look at the rate law does not include the nucleophile. It only includes the electrophile. The nucleophile is 0 order. So if I want to include it in there, I have to put a 0 here. So if I triple that, it's really like multiplying this by 3 to the 0th power. Anything to the 0th power is equal to 1. So the rate will be multiplied by 1, which means it's not going to change. So the rate would be unaffected. And the reason for that, beyond the mathematics, is because the nucleophile is not involved until after the slow step. The slow step involves loss of a leaving group. That's what's slowing the process down. Adding more nucleophile is not going to affect how often that occurs. So it does not affect how often the overall product is produced. If we want to increase the rate of product production in an SN1 reaction, we need to facilitate the loss of the leaving group. We need to make the loss of the leaving group step happen more often. And the nucleophile is not involved in that. So let's take a look at whether primary, secondary, tertiary affects the SN1 reaction. We saw that in SN2, the methyl fastest, actually we got the methyl here, the arrow opposite direction. In an SN2, the methyl was the fastest and the tertiary carbon was the slowest. And the reason for that was due to sterics, right? In the SN2, the nucleophile had to come in as the leaving group leaving, and it was blocked by sterics. It couldn't do it, and so it was a very slow reaction. In the SN1, you see the opposite. In the SN1, the methyl group is very slow, the primary is very slow, the secondary is a little faster, and the tertiary one is the fastest. And so that, again, has to do with the slow step, right? So if we want to understand this, we have to analyze the slow step of the SN1 mechanism and try to see why in one instance that step would be faster than in another instance. And so the best way to do that is to look at the reaction coordinate diagram. Right? So just to remind you, in an SN1 reaction, it's a two-step process, but the first step is a slow step. That is the key. So if forming the carbocation happens more often, then the rate will go up. And that's what we're seeing here. If the carbon is tertiary, then loss of the leaving group can happen more often. The rate of product production will happen more often because the first step where the leaving group leaves happens more often than it would if it was secondary or primary. Well, the answer, the full explanation of that requires me to look at the transition states. So we'll come back and look at those carbocations in a second. But we really want to focus on the transition state of the first step, right? The first step is a slow step. If the transition state energy is very high for that step versus lower, right? So if we have a secondary, it doesn't happen as often. The first step doesn't happen as often because the transition state is much higher in energy. So what does a transition state look like here? Well, let's try. If the leaving group's leaving, we can draw as elongated. If it's leaving, it's taking the electrons with it and becoming negative. it's pulling electrons away from the carbon. So what's bonded to the carbon? If it's secondary, there's at least one hydrogen. Well, there's one hydrogen exactly. And there's two carbon groups. And as this pair of electrons starts to leave with the leaving group, we start to create a partial positive. If it's tertiary, we see the same thing. Oops. But the difference is we'd have three carbon groups here. So assuming these are done in the same solvent, the solvent effects would be the same for both of them for the most part. So why would the transition state we've drawn here be much more stable and lower in energy than the transition state we've drawn here, right? Just to point out, these two reactions are starting at the same energy and they're ending at the same energy. The only difference is the stability during the transition state. Well, this one's not as stable because the hydrogen doesn't stabilize the positive that's forming as well as the carbon groups do. That's the key, right? So how do these carbon groups stabilize the positive? Through induction, but primarily through conjugation. We talked about that before. Let's talk about it again. So the book presents it in terms of stabilizing the carbocation, which is here at the intermediate. So forming the carbocation on a secondary carbon versus on a tertiary carbon. The more carbon groups I have there, the more the carbocation is stabilized. So the carbocation is higher energy here than over here as well. But that also applies to the transition state. And that's really the most important part, is to stabilize the transition state. That's what helps the first step happen more often, helps the overall process happen more often, giving me a faster rate of product production. So how does the carbocation become more stabilized when there's more carbon groups? Well, if there's more carbon groups, there's a bigger electron cloud, and those electrons can shift in to stabilize the positive through induction. And we can see that here. The amount of blue here is much less than the amount of blue over here. So just the general electron clouds that can kind of shift in toward that carbon through induction, through electronegativity differences to stabilize it helps. But the other part is the hyperconjugation, right? So every one of these three carbon groups can do hyperconjugation to stabilize that positive. So just to remind you there, if the carbon in the center with the positive, it's positive because there's an empty p orbital. If any one of these carbons nearby can shift a hydrogen, rotate a hydrogen into the same plane as the empty orbital, well, then the full orbital and the empty orbital overlap, and that will allow some electron density to move into that empty orbital as well, so there won't be as much positive right on that carbon. So stabilizing the positive on the carbon through shifting electrons through induction, as well as overlapping orbitals, full and empty orbitals through hyperconjugation, really helps to stabilize a full positive on a carbocation. And if the leaving group were still in the process of leaving and we were talking about the transition state on forming only a partial positive, it's still the same thing. Stabilizing a partial positive by shifting electrons through induction or overlapping orbitals through hyperconjugation also helps to stabilize that positive. So the more carbon groups I have, the more each of those factors can occur. The more induction and more hyperconjugation I can get to stabilize the positive. So if I ask you to rank stabilities of carbocations, the most stable is always going to be one that's stabilized through resonance. Don't forget that. But if none of them are stabilized through resonance, tertiary is going to be more stable than secondary, which will be more stable than primary, and I would expect you to explain how the induction and hyperconjugation work. So if you need more detailed explanation on that, please let me know. But that's the reason why the transition state and intermediates are lower in energy for the tertiary than for the secondary, and that's why the tertiary pathway happens a lot more often than the secondary. And the primary one is too slow to measure. When you only have one carbon group to shift electrons in through induction or to overlap a hydrogen with that p orbital, is there a problem with the feed here? Not seeing any messages. I was hearing a little something. I guess that's just maybe background noise. If I only have one carbon group to shift electrons through induction and through hyperconjugation where I'm overlapping the orbitals, it really can't stabilize that positive very well at all. I still have a ton of positive on carbon, very unstable. And so that would occur through such a high energy transition state that just doesn't happen often enough to even measure. So only the secondary, tertiary, or resonance stabilized carbocation can really ever form in an SN1. So make sure when you're drawing SN1 mechanisms, do not draw a primary carbocation unless it's stabilized through resonance. Real quick, in terms of the stereochemistry, if the leaving group leaves first, as we said, that creates a carbocation. And this nicely shows that it's flat. So now we can think about the nucleophile either coming in here or equal probability on the other side. And that means I would get a mixture of two different products. This shows the same thing. Once the leaving group leaves, I get a flat carbocation, so the nucleophile can attack from either side, and I get a mixture of two different enantiomers, assuming that this carbon is a chiral center. And so that's called racemization. Half the molecules are one enantiomer, half of the other. I get a racemic mixture. Because once the leaving group leaves, I don't have a chiral center anymore. There's no spatial preference for the nucleophile to come in one side or the other. And so I get both of those potential products. So let's take a quick look at this example here. What am I seeing here? I've got my leaving group. It can leave. I've got a nice strong nucleophile with a full negative on an oxygen. That's pretty unstable. That can come in. So I've also got it on a secondary carbon. That tells me that if the leaving group left first, I could create a carbocation because secondary isn't too unstable to form. But if it's secondary, it's also not too crowded usually. I've got a fairly crowded group over here, decently crowded group over here, so that might block the attack a little bit. So the SN2 is a little bit hindered by sterics. So what we see here is that some of the molecules go by SN1 and others actually go by SN2. And I know that based on the stereochemical outcome. So if I can use a polarimeter and measure the optical activity of the product mixture, and it tells me the enantiomeric excess, which I can convert into a percentage of the S enantiomer and the R enantiomer, that allows me to conclude how much of this reaction went by SN1 versus SN2. So what accounts for this? Well, I can say some goes by SN2. If it goes by SN2, the nucleophile has to attack from the back side. So since the chlorine is pointing out at me, the OH would have to come in from behind, and I would only get the R enantiomer here. So if it's occurring by SN2, I get R. If some of the reaction goes by SN1, that would involve the leaving group leaving first. I would get the carbocation, and then it would become flat. And the nucleophile could attack from the top or from the bottom. So by the SN1 mechanism, I would get 50% R and 50% S. So how much of this reaction is occurring by SN1 and how much is occurring by SN2? We can determine that mathematically. We can say the only way the S forms is through the SN1 mechanism. The only way the OH can come in on the same side where the chlorine left is if the chlorine leaves first and creates a carbocation, then the OH can come in and replace it from the same side. But anytime the carbocation forms, there's an equal probability that the OH can come in from the top or from the bottom. So for every S that's formed, there's an equal amount of R in that it's coming from that particular mechanism. So for every S that I get, there should be, out of the 65, 35% R, and that all comes from the SN1 mechanism. So 35 plus 35 is 70. So 70% of the reaction comes from the SN1. The remaining 30R must have come from the SN2, because that would come from the OH minus always coming in from the backside from where the leaving group's leaving. So I can say 30% of that came from SN2. And that makes sense because this are pretty sterically hindered groups. It's hard for the OH to get in there. Sometimes it will be able to collide there and give me strictly R, and sometimes the chlorine might leave first and give me a carbocation, and then there's a 50-50 shot as whether the OH comes in and gives me R or S. And so 70% of that mixture is a mixture of R and S, and the other 30% is just R that came only from the backside attack during the SN2 mechanism. And just to point out, sometimes we focus strictly on the products. We don't worry about what the byproducts are. Obviously, if the chlorine leaves, it's still here as a Cl minus. But if we're not interested in it, we would usually just remove that during the laboratory workup of the reaction and isolate these. So the chlorine would just, it would be gone. It would be removed, as well as the Na plus. That would probably dissolve in water and be rinsed away from the low polarity products that we would collect in a different layer in the lab. And so that leads us to the last quiz question. We're almost done here. If I want to promote an SN1, what can I do? Well, in the SN1, the first step is the key step. That's the slow step. So if I want to promote the SN1, I have to promote the loss of the leaving group. So how do I do that? Well, normally I would look to try to make the carbon it's leaving from tertiary, or make sure that when it leaves and produces a carbocation, that there's some resonance to stabilize it or something, but I don't have that option here because I'm locked in. The question tells me I'm dealing with this specific substrate. But what I can do to facilitate these collisions is to increase the molarity of this molecule. The more moles I have in a given amount of space, the more often it will be able to produce some collisions that give me the carbocation that I want. That's really the main thing there. The nucleophile isn't that important. If you wanted to say that you want to promote SN2 by trying to stop, if you want to promote SN1 by trying to stop the SN2 from occurring, you could say that you're going to use a weak nucleophile. That could be reasonable. If I use a weak nucleophile, that means it's relatively stable. And so that means it's kind of starting relatively low in energy. And so if it were to try to collide here and get through the sterics associated with these groups and produce a high energy transition state, that's not going to happen very often if the nucleophile is weak. So the SN2 mechanism wouldn't occur nearly as much with a weak nucleophile. The nucleophile would be more likely to wait around for the leaving group to leave first and produce a carbocation. So if I'm promoting the SN1, I have a high molarity of this, so it can frequently react to produce a carbocation. Then the weak nucleophile, since the carbocation doesn't have a complete noble gas configuration and it has a formal charge, it's quite unstable. So then the weak nucleophile would very easily come in there, and that next step would occur quite readily. So really the key, though, as we said, is to facilitate this first step. That's the slow step, and that would require a high concentration of this substance. It would also require me to think about how to use a solvent to facilitate the loss of the leaving group. As the leaving group leaves, that's the point I want to stabilize the most. If I can bring in a solvent to help stabilize the partial charges that form here during the transition state, I can get that whole thing to be lower in energy. Not the reactants or the products, but the pathway. It'll happen more often if it goes through a more stable transition state for that slow step. So if I wanted to experimentally verify then that it was happening by an SN1, there are two things I could do. I could confirm the racemic mixture produced, as we said over here. If it is an SN1 mechanism, and I go through a carbocation intermediate, the nucleophile has no ability to prefer one side of attack versus the other, so I get a 50-50 mixture of two enantiomers. And that would produce zero optical rotation when I put my sample in a polarimeter. Zero optical activity. And secondly, I could measure the rate law. Right? So I do the reaction, measure the rate, double the molarity of the substrate, and measure that the rate doubles. Double the molarity of the nucleophile and measure no change in the rate because the nucleophile is not involved until the second step, and that will confirm that it's zero order. So confirming the order experimentally in the rate law is another way to help confirm whether it's going by SN1 or SN2. And then this chart here just kind of summarizes a lot of what we talked about, and we're going to add more detail and see a lot of specific reactions on Thursday. Any questions about anything that we've talked about today? So here's some good practice for you to work through. Check your work with the solutions guide. Let me know if you have any questions about any of that. We're going to talk more about SN1 and SN2 on Thursday. And so make sure you prepare the quiz questions for that as early as possible. If you want to set up a time to meet with me to discuss about that, let me know. There's only a couple, I think, for you to work through, though. So hopefully you can get some decent answers for those within your groups. And that's basically it.